You were taught that the universe is smooth, that on the larger scales, if you could somehow pull back far enough, the galaxies would blur into an even haze, a mist of light spread more or less uniformly in every direction. This is the founding assumption of modern cosmology. It has a name, the cosmological principle. And for a century, it has been the floor beneath every calculation we make about the age, the size, and the fate of everything that exists. But what if the floor has a dip in it? What if the patch of universe you happen to occupy, the part you have been measuring from, the part from which every outward-looking instrument on Earth collects its data, is not typical at all? What if it is emptier than average? Significantly so, a region roughly 2 billion light-years across where the density of galaxies falls 20 to 50% below the cosmic mean. What if you have been standing at the bottom of a shallow bowl in the structure of reality and mistaking the slope beneath your feet for level ground? This is not a thought experiment. There is observational evidence, gathered across the electromagnetic spectrum from optical light to X-rays to radio waves, that the Milky Way sits near the centre of one of the largest underdense regions ever measured. It is called the KBC void, after 3 astronomers who quantified it in 2013. And its existence, if confirmed at the scale the data suggests, does not merely rearrange a few details of our cosmic address. It destabilises one of the most precise numbers in all of physics, a number on which the age and geometry of the entire universe depend. That number is the Hubble constant. I am not going to tell you the standard model is broken. I am going to walk you carefully through what the observations actually show, what they can and cannot explain, and what it would mean if the universe is lumpier than we thought on the largest scales we can see. This is a story about the ground shifting under a science that believed it had the ground well measured. And it begins with the version of the universe you were handed in school. If you find this kind of question worth sitting with, take a second to subscribe so you don't miss where this goes next. The standard story goes like this. In the beginning there was a singularity, a point of infinite density and temperature from which space and time erupted in the event we call the Big Bang. The universe expanded. It cooled. Subatomic particles condensed out of the cooling plasma. Hydrogen and helium nuclei formed in the first few minutes. Atoms assembled 380,000 years later, releasing the cosmic microwave background. Gravity slowly gathered matter into the first stars, then galaxies, then clusters and superclusters, sculpting the cosmic web we observe today. Through all of this, the expansion was uniform. The universe stretched equally in every direction, carrying the galaxies apart like raisins in a rising loaf of bread. This is the standard cosmological narrative, and it is correct in its broad strokes. But nested inside it is an assumption so deeply embedded that it is easy to mistake for a conclusion rather than a starting point. The assumption is that the expansion looks the same from everywhere. That if you measured the rate at which galaxies are receding from any point in the cosmos, you would get the same number. That our location is, cosmologically speaking, unremarkable. Part 1. The smooth universe. The cosmological principle is one of those ideas that sounds so reasonable it barely registers as an assumption. It says that on sufficiently large scales, no place in the universe is special. The density of matter, the rate of expansion, the laws governing how galaxies form and drift apart, all of these should look the same, regardless of where you happen to be standing. The universe in this view has no centre, no edge, no preferred vantage point. You could teleport to a random location 3 billion light-years away and find statistically the same kind of cosmic neighbourhood you left behind. This principle is not arbitrary. It emerged from centuries of hard lessons about the danger of assuming you occupy a privileged position. Copernicus demonstrated that the Earth is not the centre of the solar system. Galileo's observations of Jupiter's moons and Venus's phases confirmed the heliocentric model. Harlow Shapley, working at Mount Wilson in the 1910s, showed that the Sun is not at the centre of the Milky Way, but rather sits roughly 26,000 light-years from the galactic core, 2/3 of the way out along a spiral arm. And Edwin Hubble, using the same observatory in 1929, showed that the Milky Way itself is not the centre of the universe. Every distant galaxy is receding from every other, and no point is the origin of the expansion. The lesson seemed clear. Every time we assumed we were somewhere special, we were wrong. The cosmological principle formalized that humility into mathematics. And for decades, the mathematics worked beautifully. The model built on this principle, the lambda cold dark matter framework, fits an extraordinary range of observations. It correctly predicts the relative abundances of hydrogen, helium, and lithium forged in the first few minutes after the Big Bang, when the entire observable universe was a plasma denser than the centre of the Sun. It predicts the angular scale of the tiny temperature fluctuations in the cosmic microwave background, the faint afterglow of the hot early universe, measured with astonishing precision by the European Space Agency's Planck satellite, and published in its final data release in 2018. It predicts the way galaxies cluster on scales of tens and hundreds of millions of light years. It explains within the framework of cold dark matter halos how galaxies form and evolve. By almost any measure, lambda CDM is the most successful cosmological model ever constructed. It describes 13.8 billion years of cosmic evolution with fewer than a dozen free parameters. But a model that works brilliantly on average can still fail in the specific. And the specific, for us, is the patch of space we happen to be looking out from. If that patch is atypical, if the local density is significantly lower than the cosmic mean, then every measurement we make from inside it carries a bias we cannot detect from within. You would not notice the bowl if you had never climbed out of it. You would simply assume the world is flat, because every surface you have ever measured confirms the assumption. The first sign that something might be off did not come from exotic physics. It came from the simplest possible observation, counting galaxies. There is a version of this principle that is sometimes called the Copernican principle, and while the two are related, they are not identical. The Copernican principle says only that we do not occupy a special position. The cosmological principle goes further and says that no position is special, that the universe is homogeneous and isotropic on large scales. The distinction matters because you can violate the cosmological principle without violating the Copernican principle. If the universe is globally homogeneous but locally bumpy, and we happen to sit inside one of the bumps, or more precisely one of the dips, we are not in a special position in any fundamental sense. We are simply in an unusual one, the way someone standing in a valley is not at a privileged location on the Earth's surface, but is nevertheless in a spot where the ground is lower than average. The question, then, is whether our particular spot is unusual enough to matter. And matter here means unusual enough to bias the measurements we make of the universe's fundamental properties by an amount large enough to detect. For most of the history of observational cosmology, the answer was assumed to be no. The local density fluctuations, whatever they might be, were thought to average out over the volumes sampled by cosmological surveys. The Standard Model was built on this assumption, and the assumption held until two measurements of the same quantity began to disagree. Part 2, the architecture of emptiness. Before we get to the void we live in, you need to understand what the universe actually looks like at its largest scales, because the textbook description of a smooth, uniform cosmos is quietly misleading. The universe seen at its true scale resembles a sponge, or the foam on a wave, or a three-dimensional spider's web. None of these comparisons is quite right, because the geometry is more intricate than any everyday object, but they all capture the essential feature. The cosmos is not evenly filled. It is a network of dense structures woven around vast emptiness. Galaxies collect along filaments, thin threads of matter stretching across tens and hundreds of millions of light years, like the strands of an impossibly vast net. Where the filaments intersect, matter piles into dense knots, galaxy clusters containing hundreds or thousands of individual galaxies, bound together by the combined gravity of ordinary matter and vastly larger quantities of dark matter. The clusters gather into superclusters, loose associations spanning hundreds of millions of light years, though most superclusters are not gravitationally bound and will eventually be dispersed by the expansion of the universe. Between the filaments, taking up more than half the total volume of the observable cosmos, there are voids, regions where the galaxy density drops to a tenth or a fifth of the average, or less. This architecture was not predicted in advance. It was discovered piece by piece starting in the late 1970s, when redshift surveys first allowed astronomers to plot the three-dimensional positions of galaxies rather than just their locations on the flat sky. In 1978, at a symposium on large-scale structure held in Tallinn, Estonia, 4 independent groups presented evidence that the galaxy distribution is filamentary, not random. Jaanai Nasto and Mikkel Joevia from Tartu Observatory described chains of galaxies separated by conspicuous empty zones. Stephen Gregory and Laird Thompson reported a void spanning about 20 megaparsecs in the Coma and A13367 supercluster region. W. G. Tift and S. A. Gregory found similar emptiness in the Hercules supercluster. And Brent Tully and Richard Fisher described void structure around the local supercluster. The picture was consistent across all 4 analyses. Galaxies concentrate along walls and strings, with the spaces between them strikingly empty. The discovery met initial resistance. Theoretical cosmologists, particularly in the West, were unsure how filaments and voids could arise from what was assumed to be a nearly homogeneous initial state. But that skepticism faded as numerical simulations showed that gravitational instability, acting on the tiny density fluctuations present in the early universe, naturally produces exactly this filamentary, void-filled web. In 1996, J. Richard Bond, Lev Kaufman, and Dmitry Pogosyan published a landmark paper in Nature explaining how cosmic filaments are woven from the initial conditions. They showed that the characteristic web-like pattern is a generic consequence of the Gaussian random field of primordial perturbations amplified by gravitational collapse. The pioneering simulations of the 1980s, followed by the Millennium simulation in 2005, run by Volker Springel and the Virgo Consortium, reproduced the cosmic web in stunning detail. Voids, filaments, clusters, and superclusters all emerged from the same physics. By the time the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey mapped millions of galaxies in the early 2000s, the cosmic web was established fact. The typical void in these surveys has a radius of 20 to 50 megaparsecs. Voids are ubiquitous. They fill most of the volume. And they are not pathological. They are expected, ordinary, and well described by the standard model. The voids in the cosmic web are not vacuums. They are not the emptiness between atoms. They contain matter, thin wisps of gas, the occasional isolated dwarf galaxy, dark matter halos too small to host visible galaxies. But the density of galaxies inside a typical void is a factor of 5 to 10 below the cosmic mean. The contrast with the filaments and clusters that surround them is stark. If you could fly through the cosmic web, you would spend most of your time in the empty spaces, and the dense structures would flash past you like the supports of a bridge. What the standard model does not predict is a void spanning 1 billion light-years in every direction, with you sitting at its centre. And that is where this story takes its turn. Part 3. What lives inside a void. Before we encounter the specific void that may surround us, it is worth understanding what voids actually contain, because they are not the empty spaces most people imagine. A cosmic void is not a vacuum. The density of matter inside a typical void is lower than the cosmic average, by a factor of 5 to 10, but matter is still present. Dark matter halos exist inside voids, though they tend to be smaller and less massive than those found in filaments and clusters. Gas permeates the void interior, thin and hot, forming what cosmologists call the warm-hot intergalactic medium, a diffuse plasma at temperatures between 100,000 and 10 million Kelvin that is thought to contain a significant fraction of the baryonic matter in the universe, the so-called missing baryons that are unaccounted for in galaxy surveys and X-ray observations of clusters. And there are galaxies inside voids. Not many, but they are there. And they are different from the galaxies found in denser environments in ways that illuminate the role of environment in galaxy evolution. Void galaxies tend to be bluer than their counterparts in filaments and clusters, meaning they are actively forming stars at higher rates relative to their mass. They tend to be smaller, less massive, and more gas-rich. They are more likely to be late-type spirals or irregular galaxies rather than the red, dead ellipticals that dominate the cores of galaxy clusters. Their morphologies are often disturbed or asymmetric, suggesting ongoing interactions with the surrounding gas or recent episodes of star formation triggered by gas accretion. This makes physical sense. In a dense environment, galaxies are subjected to a barrage of processes that strip their gas and quench star formation. Ram pressure stripping, as they plough through the hot intracluster medium, tidal interactions with neighbouring galaxies, strangulation as their gas supply is cut off by the gravitational influence of the cluster halo. In a void, none of these processes operate effectively. Void galaxies are left alone, free to evolve in relative isolation, slowly accreting gas from their surroundings and converting it into stars at their own pace. They are, in a sense, the universe's loners, developing on their own timeline, undisturbed by the crowding and violence of denser neighbourhoods. The study of void galaxies has become its own subfield. In 2012, Rian van der Weijgaard and colleagues published a comprehensive review of void galaxy properties, drawing on data from the Sloan Digital Sky Survey's Void Galaxy Survey. They found that void galaxies are not simply scaled-down versions of field galaxies. They occupy a distinct region of the colour magnitude diagram, shifted toward bluer colours and lower luminosities, and their star formation histories differ systematically from galaxies of the same mass found in average density environments. The void, it turns out, is not just an absence. It is a distinct ecological niche producing its own characteristic type of galaxy. The evolutionary isolation of void galaxies has another consequence that matters for our story. Because void galaxies have been less perturbed by their environment, they may preserve more information about the initial conditions that gave rise to them. Their properties are a cleaner record of the primordial density field than the heavily processed galaxies found in clusters. This makes them potentially valuable as probes of cosmological parameters, including the amplitude of the initial density fluctuations on small scales and the nature of dark matter. Several ongoing surveys are targeting void galaxies specifically to exploit this diagnostic potential. The point is that voids are not featureless blanks on the cosmic map. They are regions with their own ecology, their own characteristic galaxies, and their own physical processes. Understanding what happens inside voids is essential to understanding what it means that we may live in one. Part 4, The First Great Nothing. In 1981, Robert Kirshner, Paul Schechter, Augustus Oehmler Jr. and Stephen Schechtman were conducting a survey of galactic redshifts to build a rough three-dimensional map of a small patch of sky. They worked with 3 pencil beam fields in the constellation Bootes, each separated by about 35 degrees. In all 3 fields, they found the same thing: a gap between redshifts corresponding to roughly 12,000 and 19,000 kilometers per second, approximately 125 to 200 megaparsecs away. There were no galaxies at all. This absence was not subtle. The empty zone stretched across all 3 independent lines of sight, covering a large angular area. A follow-up survey published in the Astrophysical Journal in 1987 examined 240 bright galaxies in the region between those 3 fields. A uniform distribution would have predicted 31 of them falling inside the redshift gap. None did. What they had found was a hole in the cosmos, roughly 250 to 330 million light-years across, centred about 700 million light-years from Earth. It became known as the Bootes Void, or the Great Nothing, and it was the first supervoid ever identified. The void was not a vacuum. Subsequent surveys with IRAS satellite data and targeted infrared campaigns by Gregory Aldering and collaborators eventually identified about 60 galaxies inside it, scattered along a thin tube-shaped strand running through its middle, a remnant filament that survived the evacuating process. But a region that size should hold approximately 2,000 galaxies. The void contained 3% of the expected population. The 60 galaxies inside the Bootes Void are worth a moment of attention. They tend to cluster along a single filamentary strand, running roughly through the void's centre, arranged in the pattern that emerges when smaller voids merge over cosmic time. Theoretical models suggest that the Bootes Void likely formed through the coalescence of several smaller, more typical voids, their boundaries dissolving as the combined emptiness expanded and the filaments between them thinned and broke. The few surviving galaxies are the remnants of those dissolved boundaries, galaxies that once sat on a web between smaller voids and were left stranded when the web was absorbed into the larger structure. The discovery reshaped how astronomers thought about cosmic architecture. If a void this large could exist 700 million light-years away, the universe was capable of being uneven on scales far larger than anyone had supposed. And the question of whether an even larger one might exist closer to home became not speculation, but a natural next step. The Bootes void also raised a question that would prove prophetic. Could the existence of such large voids affect cosmological measurements? In 1998, only 7 years after the void's detailed mapping, Rudnicki and colleagues speculated that if our galaxy happened to sit inside a void, the apparent expansion rate of the universe could be different from the true global rate. The idea was not taken seriously at the time. The local universe appeared to be reasonably typical, and the prevailing assumption was that any density fluctuation large enough to affect the Hubble constant would have been obvious in the redshift surveys then available. That assumption now appears to have been premature. The redshift surveys of the 1980s and 1990s mapped galaxies out to perhaps 100 or 200 megaparsecs with reasonable completeness, but the KBC void extends to 300 megaparsecs or beyond. To detect it, you needed surveys deep and wide enough to compare the local density to the density at much greater distances, and those surveys did not exist until the 2000s. The Bootes void was a warning. The universe can be very empty over very large volumes. But the warning was directed at a patch of sky 700 million light-years away, and the possibility that something similar might exist right here, right beneath our feet, was easier to set aside than to investigate. Part 5. The Void Next Door. In 1987, the same year Kirshner published his detailed confirmation of the Bootes void, Brent Tully at the University of Hawaii and his collaborator J. Richard Fisher at the National Radio Astronomy Observatory noticed something unsettling closer to home. Using redshift data from the Center for Astrophysics surveys, they mapped the distribution of galaxies in the immediate vicinity of the Milky Way and found that our galaxy sits at the edge of an extensive empty region. They called it the local void. The local void begins roughly 1 megaparsec from the Milky Way just outside the boundary of the local group of galaxies. That is about 3.26 million light-years, a distance so trivial by cosmic standards that in a scale model of the observable universe the size of a football field, the edge of the local void would be less than a millimetre from your position. The void extends outward for at least 60 megaparsecs, roughly 200 million light-years, in a direction largely blocked by the disk of our own galaxy. Most of its volume lies behind the galactic centre, obscured by dust and stars in the region called the zone of avoidance. For decades, the local void was accepted but poorly studied. Its existence was not controversial, but the obscuration made detailed mapping nearly impossible. Infrared and radio surveys peered through some of the dust, and a handful of gas-rich dwarf galaxies were found inside it. Among them a tiny system designated KK246, identified by researchers at the Special Astrophysical Observatory in Russia at a distance of about 7 megaparsecs. According to work by Nasanova and Karachentsev in 2011, the mean galaxy number density inside the local void is 5 times lower than the global average. The stellar mass density is more than 10 times below the cosmic mean. The void is not merely underpopulated. It is a desert, with the rare dwarf galaxy serving as the equivalent of a lone cactus. The picture sharpened dramatically in 2019, when Tully led a team including Daniel Pomereed, Helene Courtois, and Yehuda Hoffman in a study using the Cosmic Flows 3 catalogue, a compendium of distances and peculiar velocities for nearly 18,000 galaxies. Peculiar velocities are the motions of galaxies on top of the overall expansion, the drifts caused by gravitational pull toward dense regions and push away from empty ones. By measuring these motions and mathematically reconstructing the mass distribution, the team mapped the local void's shape, even when no telescope could see directly. The void proved more extensive than assumed. It was not a sphere but an irregular, elongated region with multiple lobes. A sparse filament threaded directly through it, from the Virgo cluster to the Perseus cluster, but the surrounding volume was empty. The void is not static. It is growing. As matter evacuates from the underdense region and piles up on surrounding walls and filaments, the void expands. The local sheet, the flat arrangement of galaxies that includes the Milky Way and forms one wall of the void, is being pushed away from the void's center. Measurements of our motion relative to the cosmic microwave background show the Milky Way moving at 631 kilometers per second, a velocity partly explained by attraction toward the Virgo cluster and the Great Attractor, but partly by a push from behind, from the emptiness of the local void. The component attributable to this push is roughly 260 kilometers per second. In 2019, Tully's team described the local void as subtending about 40% of the sky, beginning 1 megaparsec away. Tully himself wrote in the Astrophysical Journal that the average place in the universe is in a void. Most of the matter that makes up our galaxy and our neighbours must have come out of the local void, pulled outward by gravity over billions of years. Our relationship to that structure, Tully argued, is fundamental to understanding the details of the local neighbourhood. 5 years earlier, in a landmark 2014 paper published in Nature, Tully had used similar velocity mapping techniques to identify the Laniakea supercluster, the gravitational basin containing the Milky Way and roughly 100,000 other large galaxies, spanning about 520 million light-years. The name is Hawaiian, Lani for heaven, Akea for spacious. Inside Laniakea, galaxy flows converge toward a gravitational centre called the Great Attractor. The local void presses against Laniakea's boundary, shaping the motion of everything. But the local void extends only tens of megaparsecs. The cosmic web is full of voids that size. The genuine shock came when astronomers looked farther out and found that the underdensity does not end at the local void's edge. It keeps going on a scale that seemed impossible. Tully's 2019 study of the local void also revealed something unexpected about the relationship between voids and the galaxies that border them. The galaxies on the walls of the local void, including the Milky Way, are not simply sitting passively at the void's edge. They are being actively shaped by it. The gravitational influence of the void is stretching the local sheet, the thin plane of galaxies that forms our immediate neighbourhood, into a configuration that would not exist if the void were absent. The thinness of the local sheet, the fact that it is a sheet rather than a more three-dimensional structure, may itself be a consequence of the void's influence. Matter has been compressed onto the wall by the evacuation of the interior, producing a structure that is flattened perpendicular to the void's expansion. This has implications for the Milky Way's own history. The infall of gas from the void's direction, combined with the push of the void's expansion, may have influenced the angular momentum of our galaxy, the rate of gas accretion onto the disk, and even the timing of major merger events. The local void is not just a feature of the background. It is part of the environment that shaped the galaxy we live in. There is a philosophical dimension to this that is worth noting. We tend to think of the Milky Way as existing in space, as though space were a neutral container and the galaxy were an object placed inside it. But the void tells a different story. The galaxy exists in a particular density environment, and that environment is part of what made the galaxy what it is. The emptiness is not just surrounding us. It is in a real physical sense part of us. Part 6, the billion light-year hole. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie at the University of Hawaii published a paper in the Astrophysical Journal that would become one of the most debated results in modern cosmology. They had set out to measure how the density of galaxies changes with distance from our location. They used the 2M++ galaxy catalogue, combining photometric data from the 2-micron all-sky survey with spectroscopic redshifts from the Sloan Digital Sky Survey, the 2-micron redshift survey, and the 6-degree field galaxy redshift survey. Their measurement was the K-band galaxy luminosity function, a count of how many galaxies of each brightness exist within a given volume, computed at different distances. Near-infrared photometry in the K-band is particularly well suited for this task, because it traces the stellar mass of galaxies directly, penetrating the dust that obscures shorter wavelengths. K-band luminosity is a reliable proxy for the underlying matter distribution, making it less sensitive to the vagaries of star formation rates that can inflate or suppress optical counts. What Keenan, Barger and Cowie found was that the luminosity function in the local universe, out to about 300 megaparsecs from the local group, was significantly depressed compared to the function at greater distances. The density of galaxies in our neighbourhood was roughly half the cosmic mean. not marginally below average, half. The deficit was visible across nearly 90% of the observable sky and appeared in multiple independent slicings of the catalogue, by galaxy counts, by luminosity density, by stellar mass. Beyond 300 megaparsecs, the counts returned to normal. The underdensity was bounded. It had edges. It was a void, centered approximately on our position, with a radius of about 1 billion light-years. This is the feature that became known as the KBC void. 1 billion light-years is not a typical void radius. The average cosmic void spans 20 to 50 megaparsecs. The Bootes void has a radius of about 62 megaparsecs. The KBC void is roughly 7 times larger. Its full diameter of approximately 2 billion light-years represents around 2% of the diameter of the observable universe. If you were to superimpose it on a map of all the known cosmic structure, it would swallow the Laniakea supercluster, the Virgo cluster, the Great Attractor, the Perseus-Pisces supercluster, and large swathes of the cosmic web, all fitting within a single underdense region. Earlier hints had accumulated. In 1990, Simon Maddox, Will Sutherland, George F. Stathieu, and John Loveday found evidence of a local deficit in optical galaxy counts. In the late 1990s, William Frith, Nigel Metcalfe, and Tom Shanks in Durham traced the underdensity using infrared surveys. In 2012, Igor Karachentsev found the average mass density within 50 megaparsecs of the local group to be a factor of 3 to 4 below the lambda CDM prediction. In 2014, John Whitbourne and Tom Shanks found a 15% underdensity extending to 150 to 300 megaparsecs. In 2022, Jenny Wong, Shanks, Metcalfe, and Whitbourne confirmed the deficit across 90% of the sky to about 200 megaparsecs. X-ray cluster surveys by Hans Bohringer, Guyong Chon, and Chris Collins showed the same pattern. Radio surveys by Matthias Rubart and Dominic Schwartz agreed. A local underdensity was evident across the entire electromagnetic spectrum: optical, infrared, X-ray, radio. Multiple independent teams with different instruments and methods converged on the same conclusion. The region we inhabit is noticeably emptier than the cosmos at large. Sit with that. Not the fact that voids exist. The fact that this void, if real at its claimed scale, places the Milky Way in a statistically exceptional location. A place that the cosmological principle says should not be special. The K-band luminosity function that Keenan, Barger and Cowie measured deserves a closer look, because the methodology reveals both the strength and the limitations of the void claim. The luminosity function is essentially a census: how many galaxies exist at each level of intrinsic brightness within a given volume. In a homogeneous universe, the luminosity function should be the same everywhere, after correcting for the evolution of galaxy properties with cosmic time, a correction that is small at the low redshifts involved. If you measure the luminosity function locally and compare it to the function at larger distances, any difference reveals a density fluctuation. Keenan, Barger and Cowie divided their survey volume into radial shells and computed the luminosity function in each shell. In the innermost shells, out to about 300 megaparsecs, the function was systematically depressed at all luminosities. This is important. If the deficit were confined to faint galaxies, it could be explained by incompleteness in the catalogue, since faint galaxies are harder to detect at large distances. But the deficit was present at all magnitudes, including the brightest galaxies, which are complete in the surveys out to well beyond 300 megaparsecs. The underdensity was not an artifact of survey depth. It was a real deficiency of galaxies across the full brightness range. The 2M++ catalogue they used is not a single survey, but a composite. It stitches together the 2-micron all-sky survey, the 6-degree field galaxy redshift survey, and the Sloan digital sky survey. Each of these surveys has its own photometric calibration, its own selection function, and its own incompleteness characteristics. Keenan, Barger and Cowie tested their results against these individual surveys and found the underdensity visible in each one independently. They also tested whether the deficit could be an artifact of the survey geometry, the angular mask or the photometric 0 point, and found that none of these could explain it. The convergence of the luminosity function to its global value beyond 300 megaparsecs is perhaps the most striking feature of their result. It means the underdensity has a boundary. It is not a gradual monotonic increase in density with distance, which could reflect a systematic error in the distance calibration, but a transition from low density to normal density at a specific radius. This transition is the edge of the void, and its sharpness constrains the density profile. The void is not a shallow, featureless gradient, but a bounded structure with an interior significantly emptier than its exterior. Part 7. The distance ladder rung by rung. The Hubble tension cannot be understood without understanding how the distance ladder actually works, because the details matter enormously for assessing whether the local measurement could be biased. The problem of cosmic distances is, at its core, a problem of calibration. The universe provides no ruler marks. There are no mile markers between galaxies. Every distance measurement in extragalactic astronomy depends on identifying objects whose intrinsic properties are known well enough that their apparent properties reveal how far away they are. The first rung of the ladder is geometric. Within the Milky Way and its immediate neighbours, distances can be measured directly using parallax, the apparent shift in a star's position on the sky as the Earth moves from one side of its orbit to the other. The size of this shift, measured in arc-seconds, gives the distance in parsecs, a parsec being the distance at which a star shows 1 arc-second of parallax, about 3.26 light-years. The European Space Agency's Gaia satellite, launched in 2013 and still operating, has measured parallaxes for nearly 2 billion stars in the Milky Way with micro-arc-second precision, providing a geometric foundation for the entire ladder that is essentially immune to systematic error. The second rung uses Cepheid variable stars. Cepheids are massive, luminous, pulsating stars that brighten and dim with a regular period ranging from a few days to a few months. In 1908, Henrietta Swan Leavitt, working at the Harvard College Observatory as a computer analysing photographic plates of the Magellanic Clouds, discovered that the pulsation period of a Cepheid is directly related to its intrinsic luminosity. Brighter Cepheids pulsate more slowly. This period-luminosity relation means that if you can measure a Cepheid's period, which is easy, you just watch it blink. And its apparent brightness, also straightforward, you can calculate its distance. Cepheids are bright enough to be seen in galaxies tens of megaparsecs away, making them the workhorse of extragalactic distance measurement. The SH0ES team, led by Adam Rees, calibrates the Cepheid period luminosity relation using Gaia parallaxes for Milky Way Cepheids and geometric distances to nearby galaxies, including the Large Magellanic Cloud, NGC 42558, with its water megamesa, and M31. They then observed Cepheids in galaxies that also hosted type Ia supernovae, creating a bridge between the Cepheid distance scale and the supernova distance scale. The third rung, and the one that reaches farthest, uses type Ia supernovae. These are the thermonuclear explosions of carbon-oxygen, white dwarf stars, that have accumulated mass from a companion star until they reach the Chandrasekhar limit of about 1.4 solar masses, at which point nuclear fusion reignites catastrophically, and the star is destroyed in a few seconds. Because the explosion mechanism is thought to be similar in each case, the mass at detonation is always about the same. The peak luminosity of a type Ia supernova is roughly standard, though it varies with the light curve shape in a well-characterized way discovered by Mark Phillips in 1993. Brighter supernovae decline more slowly, dimmer ones decline faster. By measuring the light curve shape and the apparent peak brightness, you can determine the distance. Type Ia supernovae are extraordinarily bright, briefly outshining their entire host galaxy, and they can be detected at redshifts well beyond 1, corresponding to distances of billions of light-years. The Hubble constant is derived from the slope of the relationship between supernova distances and the recession velocities of their host galaxies, measured in a redshift range, roughly 0.023 to 0.15, where the expansion is well into the Hubble flow, but not yet complicated by the need for detailed cosmological corrections. The critical point for our story is that the Cepheid calibration and the low redshift supernova that anchor the Hubble constant measurement all sit within a few hundred megaparsecs of the Milky Way. If that volume is underdense, and if the underdensity is generating a coherent outward flow, then the recession velocities of the host galaxies are not purely cosmological. They include a component from the void's outflow, and that component would steepen the Hubble diagram, pushing the measured h0 upward. Alternative distance indicators provide independent checks. The tip of the red giant branch, TRGB, uses the sharp cutoff in the luminosity of red giant stars just before they undergo the helium flash. This cutoff occurs at a nearly universal luminosity and can be used as a standard candle. Surface brightness fluctuations exploit the granularity of unresolved stellar populations in elliptical galaxies. Megamesa distances use the geometry of water mesas, orbiting supermassive black holes in active galaxies, NGC 4258 being the gold standard. Each method has its own systematics, its own strengths, and its own vulnerabilities to local structure. The fact that all of them give H0 values closer to 73 than to 67 is what makes the tension so stubborn. But all of them also sample the same local volume, and all of them would be affected by the same void-induced outflow. This is why the KBC void matters so much for the Hubble tension. It is not enough to check one rung of the ladder. You have to ask whether the entire ladder is planted on tilted ground. Part 8. Two rulers, two numbers. In 1929, Edwin Hubble published a graph that became one of the most consequential diagrams in science. It plotted galaxy distances against recessional velocities and showed a roughly linear relationship. The farther a galaxy, the faster it recedes. The slope of that line, the Hubble constant h0, encodes the present expansion rate of the universe. Every additional megaparsec of distance adds a fixed increment of recessional velocity. The Hubble constant looks simple. It is a ratio of speed to distance. But from it you can derive the age of the cosmos, calculate whether the universe is geometrically flat or curved, and predict the fate of all matter and energy. H0 is the linchpin. Get it wrong, and the architecture shifts. For decades, measuring it accurately was the central challenge. Galaxy distances are difficult to establish, and H0 remained uncertain by a factor of 2 for much of the 20th century. But by the 2000s, two independent methods had become precise enough that their values should agree. They do not. The first looks backward to the infant universe. The cosmic microwave background, released 380,000 years after the Big Bang, carries temperature fluctuations imprinted by primordial sound waves. Their angular scale, measured by Planck, allows cosmologists to reconstruct the early universe and predict today's expansion rate using lambda CDM. The answer 67.4 plus or minus 0.5 kilometers per second per megaparsec. The second looks at the local universe directly. It builds a distance ladder from Cepheid variable stars, whose pulsation periods relate to their luminosity, a relationship calibrated by Henrietta Swan-Leavitt in 1908, up through type Ia supernovae, thermonuclear explosions of white dwarfs bright enough to see across billions of light years. The most precise version from Adam Maurice and the SH0ES team using Hubble and JWST gives 73.17 plus or minus 0.86, reported by Bruval and colleagues in 2024. The gap's about 9%. The disagreement now exceeds 6 sigma, making it less than 1 in a billion, probable as a fluke. A 7 sigma tension was subsequently reported by the H0 Distance Network collaboration. At an American Astronomical Society meeting in January 2025, Dan Skolnick of Duke University called it a crisis. The SH0ES team used JWST to reobserve T-feeds that Hubble had measured, testing whether crowding or dust biased the distances. The JWST data matched. Other teams reached similar values using different ladder rungs: tip of the red giant branch, surface brightness fluctuations, megamesa distances, type 2 supernovae. The local measurement is robust across methods. In March 2025, Wendy Friedman and the Carnegie-Chicago Hubble program reported a JWST value closer to the CMB prediction using the red giant branch. Debate followed. Skolnick noted the result sits in the middle of the tension and questioned sample exclusions. The community remains divided. But there is a possibility that neither side reckoned with. What if neither measurement is wrong? What if the universe genuinely expands at 67 globally and appears to expand at 73 from our location. What would make both numbers correct? A void, a large local underdensity creating a localized excess in the apparent expansion rate. Real, physical, consistent with a lower global rate. And that is exactly what the KBC void could provide. Part 9. The physics of a hollow. To understand how a void inflates the local Hubble constant, you need one piece of physics, and it is not exotic. It is gravity. In a homogeneous universe, every patch expands at the same rate, but the universe is not homogeneous. A galaxy inside an overdense region feels a net inward gravitational pull from surrounding mass, slowing the local expansion. A galaxy inside an underdense region feels the opposite, a net outward tug toward the denser walls and filaments. Matter flows away from the void's centre toward the denser surroundings, and this outward flow adds to the cosmic expansion. Imagine a river flowing downstream. On a flat stretch, the current is predictable. But where the riverbed dips into a depression, the water accelerates as it flows out. You measure a faster current in the dip. An observer on level ground downstream measures the true average. You in the hollow get a biased reading. This is the shallow bowl I want you to hold for the rest of this conversation. You are at the bottom. The outward flow of matter adds a boost to the expansion rate you measure. The universe is not expanding faster here in any fundamental sense. The same global rate applies. But your instruments pick up the extra motion of galaxies fleeing the void, and that motion masquerades as a higher Hubble constant. The boost depends on the void's depth and extent. In 2020, Moritz Hasselbauer, Indranil Banik, and Pavel Krupa at the University of Bonn published a detailed model in monthly notices of the Royal Astronomical Society. Hasselbauer, then a PhD student, and Banik, who had joined as an Alexander von Humboldt Fellow in 2018, treated the void as a sphere with the density contrast measured by Keenan, Barger and Cowie, about 46% below the cosmic mean, extending to 300 megaparsecs. They calculated the outward flow this would produce, a boost of approximately 11% in the locally measured Hubble constant. 11%, almost exactly the gap between 67 and 73. The local measurement captures the true global rate plus the void flow. The CMB captures the global rate alone, both correct. This requires no new particles, no modified gravity, no exotic early universe physics. It uses gravity and the observed density of the local universe. If we live inside a void large enough and deep enough, the Hubble tension dissolves. But Hasselbauer, Banik and Krupa ask the next question. Is such a void consistent with the standard model? No. The physics of void-induced outflow has a name in the technical literature, the super-Hubble flow. It refers to the component of a galaxy's recessional velocity that exceeds the global Hubble flow due to the galaxy's position inside a void. The super-Hubble flow is not a violation of the Hubble law. It is an addition to it, a local perturbation on top of the global expansion caused by the gravitational dynamics of the void. In a perfectly compensated void, one where the mass missing from the interior has been redistributed to a dense shell at the boundary, the super-Hubble flow inside the void is exactly offset by a sub-Hubble flow outside it, and the global average is preserved. But a void does not need to be perfectly compensated for the super-Hubble flow to bias local measurements. The key parameter is the density contrast, usually denoted delta, defined as the difference between the local density and the cosmic mean divided by the cosmic mean. A delta of negative 0.46, the value reported by Keenan, Barger and Cowie for the KBC void, means the local density is 46% below the mean. The super-Hubble flow produced by such a void can be calculated analytically in the linear regime, where the density contrast is small enough that perturbation theory applies, and numerically in the nonlinear regime, where the contrast is large enough that nonlinear gravitational effects become important. For a void with delta around negative 0.2, the linear approximation is adequate. For delta around negative 0.46, nonlinear corrections become significant, and the actual outflow is somewhat larger than the linear prediction. Hasselbauer, Banik, and Krupa performed their calculation in the nonlinear regime using a numerical integration of the void dynamics. Their result, an 11% boost in the locally measured Hubble constant, is robust to the specific assumptions about the void's density profile, top hat versus Gaussian versus exponential, though the exact number varies by a percent or two depending on the profile shape. The important point is that the boost is of the right order of magnitude to explain the Hubble tension, regardless of the detailed assumptions. Part 10. Too big for the box. Lambda CDM makes specific predictions about cosmic lumpiness on any given scale. The power spectrum of initial density fluctuations stretched by inflation and amplified by gravity over 13.8 billion years sets hard limits on how deep and how large a void can be at the present epoch. On scales of several hundred megaparsecs, the expected cosmic variance in density is only a few percent. Hasselbauer, Banach and Krupa tested the KBC void against the MXXL simulation, one of the largest lambda CDM simulations ever run, a cube 4.1 gigaparsecs on a side. They searched for regions matching the KBC void's size and depth, a sphere of 300 megaparsecs, with a density 46% below the mean. They found none. Not one region in the entire simulation volume came close. The probability, they calculated, represents a tension of 6.04 sigma. The cosmic variance on 300 megaparsec scales in lambda CDM is only about 4.8% in redshift space. Observations across 90% of the sky show a deficit of 20 to 50%. The discrepancy is vast. This is the dilemma. The void could solve the Hubble tension, but if it is real at the claimed depth, it breaks the standard model. One crisis replaces another. Hasselbauer and Banach proposed a resolution in Milgromian dynamics, the modification of Newtonian mechanics first advanced by Mordechai Milgrom in 1983 to explain galaxy rotation curves without dark matter. In their NUHDM framework, incorporating hot dark matter via a sterile neutrino of 11 electron volts, structure formation is more efficient. Stronger effective gravity allows the small primordial fluctuations to grow into deeper voids and denser filaments. The KBC void arises naturally. In 2023, Niels Wittenberg and colleagues in Bonn published the first hydrodynamical simulations of structure formation in the NUHDM model, showing that the same physics that produces deeper voids also generates the concentrated, clumpy galaxy distribution observed in reality. Elena Asensio and Banach had shown that the massive galaxy cluster El Gordo, observed at redshift 0.87, occurs naturally in this framework but is extremely unlikely in lambda CDM. This proposal is radical. MOND has never gained mainstream acceptance in cosmology. Dark matter is considered established science, supported by the CMB, gravitational lensing, and cluster dynamics. But the proposal exists because the alternative, a 6 sigma anomaly within the standard model, is also deeply uncomfortable. Let me be precise. The local underdensity is well supported. Its approximate depth and extent are consistently measured. What is debated is whether the void is as deep, as large, and as sharply bounded as the most extreme claims suggest. There is a subtlety in the MXXL comparison that is worth unpacking, because it reveals how delicate the tension calculation actually is. The MXXL simulation was run using cosmological parameters from the first-year data release of the Wilkinson Microwave Anisotropy Probe, published in 2003. These parameters differ in several respects from the Planck 2018 values that represent the current best estimates. In particular, the WMAP1 parameters include a higher value of sigma 8, the amplitude of matter fluctuations on 8 to megaparsec scales, and a different spectral index for the primordial power spectrum. Both of these affect the predicted abundance of large voids. A higher sigma 8 produces more structure on all scales, including larger voids, while a different spectral tilt changes the relative amount of power on large versus small scales. Hasselbauer, Banach and Krupa argued that the WMAP1 parameters used in MXXL actually favour more structure formation than the Planck parameters, meaning that the tension with the KBC void would be even worse in a simulation using Planck cosmology. But this argument has been disputed. The relationship between the cosmological parameters and the void abundance on 300 megaparsec scales is not linear, and it depends on the details of how voids are defined and identified in the simulation. Different void-finding algorithms, watershed, spherical overdensity, Zoboff, can give different void sizes and depths for the same underlying density field, and the choice of algorithm affects the statistical comparison. Moreover, the MXXL simulation, while enormous, represents only one realization of the lambda CDM universe. Cosmic variance at the level of the simulation volume itself introduces uncertainty into the void abundance statistics. A different random seed for the initial conditions would produce a different arrangement of voids, and it is possible, though unlikely, that a particularly deep void on 300 megaparsec scales could arise in some realizations, but not others. The Jubilee simulation, another large lambda CDM run, has been used in complementary analyses with broadly consistent results, but the void statistics on the larger scales remain limited by the number of independent volumes that have been simulated. The bottom line is that the 6 sigma tension quoted by Hasselbauer and colleagues is likely to be approximately correct, but its exact value is sensitive to choices in methodology that reasonable researchers can disagree about. What is not in dispute is that a void of the size and depth claimed for the KBC void would be very rare, probably unrealizably rare, in a standard lambda CDM universe. The debate is over whether very rare means 5 sigma, 6 sigma, or 4 sigma, and whether any of these constitutes a genuine falsification of the model. Part 11. The Skeptics. Not everyone is convinced that the KBC void is as significant as its proponents claim. The counter-arguments are grounded in data. In 2025, Richard Stiskalek, Harry Desmond, and Indranil Banik himself published an analysis in monthly notices using the Thule-Fisher catalogue from Cosmic Flows 4. Rather than counting galaxies, they used direct distance measurements based on the relationship between a spiral galaxy's rotation speed and its luminosity. These geometric distances map the actual velocity field, independent of the Hubble flow. The velocity field shows evidence for a local underdensity, but the preferred void size is significantly smaller than 300 megaparsecs. Depending on the density profile, the best-fitting void is about 10% of the fiducial size. A void that small contributes outward flow, but not enough to close the Hubble tension. This does not make the KBC void fictitious. It suggests the relationship between galaxy counts and mass distribution is more complicated than a spherical model implies. The real universe is messy, filamentary, anisotropic. A galaxy count analysis captures the average deficit, but cannot reveal detailed three-dimensional structure. The velocity field approach captures dynamics directly, but is limited by the number of accurate Thule-Fisher distances. There is also a question of consistency with baryon acoustic oscillation data. In 2025, Banik and Vasileios Kalaitsidis tested the void hypothesis using 20 years of BAO measurements. If the local universe is underdense, the BAO signal at low redshifts should be systematically distorted. They found the data consistent with a void, but not precise enough to distinguish large from small. Martin Salin and colleagues have argued that the statistical tension depends sensitively on how the void is defined. With different assumptions about shape and boundary, the disagreement with lambda CDM weakens. The debate is technical, ongoing, and turns on survey design, selection effects, and density estimators. The underdensity is real. The depth, extent, and cosmological implications are genuinely unsettled. The distinction between galaxy counts and the velocity field as probes of the void is one of the most important technical details in this entire debate, and it deserves more attention than it usually receives. Galaxy counts tell you how many galaxies are present in a given volume. If you find fewer galaxies than expected, you infer an underdensity. But galaxy counts can be affected by several factors that have nothing to do with the total amount of matter present. Dust obscuration can hide galaxies. Photometric calibration errors can cause galaxies to be misclassified or missed. Selection effects in spectroscopic surveys can bias the sample toward or away from certain types of galaxies. And most importantly for the KBC void debate, redshift space distortions can move galaxies' apparent positions along the line of sight, compressing over densities, the fingers of God effect, and expanding under densities. The velocity field, by contrast, responds directly to the gravitational influence of the total mass distribution, including dark matter, which makes up about 85% of the matter in the universe and is not visible in galaxy counts. If a region is underdense in total mass, including dark matter, the surrounding galaxies will flow away from it in a measurable way. The velocity field is therefore a more direct probe of the underlying density contrast than galaxy counts, but it has its own limitations. Peculiar velocities are difficult to measure accurately. They require independent distance indicators, like the Tully-Fisher relation, and the current sample of galaxies with reliable peculiar velocity measurements is much smaller than the sample of galaxies with measured redshifts. The fact that the velocity field analysis by Stiskellek, Desmond and Bannock finds a smaller void than the galaxy count analysis does not necessarily mean the galaxy count analysis is wrong. It could mean that the relationship between galaxy density and total mass density is more complex than the simplest models assume, a phenomenon known as galaxy bias. If galaxies in the local universe are underrepresented relative to the total mass, perhaps because the low density environment of the void suppresses galaxy formation, as void ecology studies suggest, then the galaxy count deficit could be larger than the total mass deficit, and both measurements could be correct, measuring different things. Resolving this ambiguity requires either a much larger sample of peculiar velocity measurements, which Cosmic Flows 5 and future surveys will provide, or an independent probe of the total mass distribution, such as weak gravitational lensing, which Euclid and Rubin will provide. Until then, the true depth of the KBC void remains genuinely uncertain, and both the galaxy count and velocity field results should be taken seriously as bounds on the range of possibilities. Expand coda tabao 2. I said at the beginning that this is a story about the ground shifting. Let me return to that image one more time. In geology, there is a phenomenon called subsidence, the gradual sinking of the ground surface due to the removal of material beneath it, whether by mining, groundwater extraction, or the natural dissolution of limestone. The process is often imperceptible from day to day. The ground looks solid. Buildings stand, roads remain level. But over years and decades, the surface drops, and eventually the consequences become visible. Cracks in foundations, tilted walls, roads that no longer drain properly. The ground was never as solid as it appeared. It was slowly, quietly giving way beneath the infrastructure that depended on it. The KBC void, if it is confirmed, is the cosmological equivalent of subsidence. The ground on which we built our measurements, the assumption that the local expansion rate equals the global one, was never as solid as it appeared. It was a reasonable assumption, supported by the best data available, and for decades it produced results that seemed consistent and reliable. But the precision of the measurements eventually exceeded the precision of the assumption, and the cracks appeared. The Hubble tension, the bulk flow anomaly, the quasar dipole. Each crack individually could be explained away. Together they form a pattern that points downward, toward the hollow beneath the surface. Whether the hollow is deep enough to explain the cracks is still an open question. But the fact that we are asking the question at all, that we have instruments sensitive enough to detect a 20% density fluctuation on a scale of 1 billion light-years, that we can stand inside a cosmic hole and figure out that we are in one. That is a testament to the extraordinary precision of modern science and to the relentless, patient, century-long project of mapping the universe from the inside out. The bowl may be shallow, but we felt it, and that in itself is remarkable. Part 12, the rivers that run too fast. If the KBC void produces an outward flow, that flow should appear in the peculiar velocities of galaxies over large scales. This is the bulk flow, the average streaming motion within a given volume after subtracting the Hubble expansion. A large, coherent flow exceeding lambda CDM's prediction is a problem for the model. The data is troubling. In 2023, Sergei Mazurenko, Bannock, Krupa, and Hasselbauer showed that a local void model could simultaneously explain the Hubble tension and the observed bulk flow within 250 megaparsecs. The observed flow at that scale is significantly larger than what the lambda CDM power spectrum produces. A deep local void generates exactly this kind of coherent streaming. The issue has a longer history. In 2009, Richard Watkins, Hume Feldman, and Michael Hudson reported consistently large cosmic flows on 100 megaparsec scales, calling them a challenge for the standard model. Subsequent analyses with Cosmic Flows 3 and Cosmic Flows 4 have sharpened the tension. The flows are real, large, and directionally consistent with our position inside an underdense region. There is also the dipole anomaly. The cosmic microwave background shows a temperature dipole caused by our 370 km per second motion through the CMB rest frame. The standard interpretation is kinematic. If correct, distant matter should show a matching dipole with consistent amplitude. In 2022, Nathan Seacrest and colleagues measured the dipole in over 1 million cat-wise quasars. The direction matched. The amplitude exceeded the kinematic prediction by more than a factor of 2, at over 4 sigma. This has been debated but not overturned. A larger than expected matter dipole, if real, implies the distribution of matter is not as isotropic as the cosmological principle requires. A large local void is one candidate explanation. Our position inside the void contributes an extra velocity component that inflates the apparent dipole. No single observation here is conclusive, but the pattern is notable. Multiple independent measurements, using different data sets and techniques, point the same way. The local universe appears less dense, less smooth, and less isotropic than the standard model expects. Whether this reflects a genuine failure of the model or a statistical fluctuation at the edge of what it allows is an open question. The bulk flow problem has a longer and more contentious history than most popular accounts suggest. In 2008, Alexander Kashlinsky, Fernando Atrio Barandella, Dale Kochevsky, and Harold Ebling published a provocative paper claiming to have detected a dark flow, a large-scale coherent motion of galaxy clusters extending to at least 800 megaparsecs, using the kinematic Sunyaev-Zeldovich effect, the slight spectral distortion of CMB photons scattered by the hot gas in galaxy clusters. They interpreted this as evidence for matter being pulled toward a mass concentration beyond the observable horizon, a relic of pre-inflationary structure. The claim was controversial and was disputed by the Planck collaboration in 2014, which found no evidence for the dark flow in their own analysis of the kinematic Sunyaev-Zeldovich signal. But the absence of a dark flow in the Planck data does not resolve the bulk flow tension, which is a different and more subtle problem. The bulk flow measured by cosmic flows and other peculiar velocity surveys is the coherent streaming of galaxies within a few hundred megaparsecs, not the much larger scale dark flow that Kashlinsky proposed. The cosmic flow's bulk flow is consistently larger than the lambda CDM expectation on scales of 100 to 250 megaparsecs, but it does not extend to the horizons required by the dark flow hypothesis. The two claims are distinct, and the failure of the dark flow claim does not weaken the bulk flow evidence. The relationship between the bulk flow and the KBC void is important because the void provides a natural explanation for the excess flow. In a void model, matter flows outward from the underdense centre toward the denser walls, producing a coherent streaming pattern that is strongest near the void's centre and diminishes toward the edges. The direction and magnitude of the observed bulk flow are consistent with this picture. Mazurenko and colleagues showed in 2023 that the same void parameters that resolve the Hubble tension also predict a bulk flow amplitude and direction that matches the cosmic flow's data. This is not a trivial result. The Hubble tension and the bulk flow are measured using completely different techniques and different galaxy samples, so the fact that a single void model can explain both simultaneously is a significant point in favour of the void hypothesis. Part 13. The ground shifts under dark energy. The KBC void is not the only reason to suspect something is off. While the Hubble tension consumed attention, quite a revolution unfolded in the study of dark energy. In April 2024, the Dark Energy Spectroscopic Instrument released its first-year results. DESI, mounted on the Mayall telescope at Kitt Peak, records 5,000 spectra simultaneously and will map over 40 million galaxies and quasars. Its baryon acoustic oscillation measurements at different redshifts constrain the properties of dark energy with precision no previous instrument could achieve. Since 1998, when two supernova teams led by Saul Perlmutter and by Brian Schmidt and Adam Rees, discovered accelerating expansion, the simplest explanation has been a cosmological constant, a fixed energy density, unchanging over time, the lambda in lambda CDM. Its equation of state parameter W should equal exactly -1, always. The DESI Year 1 data showed a preference for W that is not constant. Dark energy appeared to be weakening over time. The significance was 2 to 3 sigma. Then in March 2025, DESI released Year 3 results with triple the data. The preference strengthened. Combined with CMB and supernova datasets, significances ranged from 2.8 to 4.2 sigma. Mustafa Ishak Bushaki of UT Dallas, co-chair of DESI's parameter group, said the result was approaching the point of no return. Willem Elbers, a postdoctoral researcher at Durham and co-chair of the same group, said the data suggested potential cracks in the standard model. Dynamic dark energy does not directly explain the void or the Hubble tension, but it deepens the unease. And the two might connect. A universe where dark energy was weaker in the past would have experienced prolonged gravitational growth, allowing deeper voids to form before dark energy suppressed further structure formation. The void puzzle and the dark energy puzzle could share a root. The model is not ruined. It remains the best fit to the broadest data, but it faces pressure from multiple fronts simultaneously: the Hubble tension, the KBC void, the bulk flow, the quasar dipole, the DESI hints. No single observation has reached 5 sigma. But 3 and 4 sigma tensions accumulating from independent directions are difficult to dismiss. There is a broader context for the DESI results that is worth noting. The question of whether dark energy is truly constant has been a central concern of observational cosmology since the discovery of accelerating expansion. If W equals exactly -1, dark energy is a cosmological constant, and its origin might be traced to the vacuum energy of quantum field theory. But the vacuum energy predicted by quantum field theory is roughly 120 orders of magnitude larger than the observed dark energy density, a discrepancy so vast that it is sometimes called the worst prediction in the history of physics. If dark energy is not a cosmological constant, if W differs from -1 or changes over time, then the vacuum energy explanation fails and some other mechanism must be at work. The DESI data tentatively suggests that W was less negative, closer to 0, in the recent past and is approaching -1 now, meaning dark energy was weaker a few billion years ago and has been strengthening. This behaviour is qualitatively consistent with a class of theoretical models called quintessence, in which dark energy is not a constant, but a slowly evolving scalar field rolling down a potential energy landscape. Different quintessence models predict different trajectories for W, and the DESI data, if confirmed with higher significance, could begin to discriminate among them. The connection to the void story is indirect but important. If dark energy has been evolving, the expansion history of the universe is different from what lambda CDM assumes, and the growth of structure, including the formation of voids, would have proceeded on a different timeline. A universe with weaker dark energy in the past would have experienced more gravitational clustering at intermediate redshifts, potentially producing deeper voids at the present epoch. This does not prove that the KBC void is real or that it was caused by evolving dark energy, but it opens a theoretical pathway that connects the void puzzle to the dark energy puzzle in a way that pure lambda CDM does not allow. Part 12. The cold spot in the shadow of absence. There is one more piece of evidence that bears on the question of large-scale cosmic voids, and it comes not from galaxy surveys, but from the cosmic microwave background itself. In 2004, Patricio Vielva and colleagues at the University of Cantabria, analysing data from the Wilkinson Microwave Anisotropy Probe, identified an anomalously cold region in the CMB centred in the constellation Eridanus. The cold spot, as it became known, spans about 10 degrees on the sky, roughly 20 times the angular diameter of the full moon, and is colder than the surrounding CMB by about 70 microkelvins after the standard cosmological dipole and foreground contamination have been removed. Its statistical significance has been debated, but it is one of several anomalies in the CMB that do not have an obvious explanation within the standard model. One proposed explanation is that the cold spot is the imprint of a supervoid along the line of sight. When CMB photons travel through a void, they experience the integrated Sachs-Wolf effect. They gain energy falling into the void's gravitational potential well and lose energy climbing back out. But because the universe is expanding and dark energy is accelerating that expansion, the potential well has become shallower by the time the photon exits. The photon loses slightly more energy leaving than it gained entering, producing a net cooling. The effect is small for any individual photon, but integrated over a large void, it can produce a measurable cold spot in the CMB. In 2015, Istvan Sapudi and colleagues at the University of Hawaii, the same institution where the KBC void was characterized, reported the detection of a supervoid aligned with the cold spot, using photometric redshift data from the Pan-STARRS-1 and WISE surveys. The supervoid they identified spans about 220 megaparsecs in radius and is centered at a redshift of roughly 0.22, placing it about 3 billion light-years away. It is one of the largest individual voids ever detected by galaxy surveys. However, subsequent analyses have shown that the supervoid identified by Sapudi and colleagues is probably not deep enough to fully explain the cold spot through the integrated Sachs-Wolf effect alone. The predicted temperature decrement from the ISW effects in a void of that size and depth is only about 20 microkelvins, roughly a third of the observed anomaly. Either the void is deeper than the photometric surveys suggest, or additional physics is at work, or the cold spot has a different origin entirely, perhaps a rare but not impossible primordial fluctuation. The cold spot connection matters for the KBC void story because it demonstrates that supervoids can leave observable imprints on the oldest light in the universe. If a void 220 megaparsecs in radius can produce a detectable temperature anomaly in the CMB, the question of what effect a 300 megaparsec void centered on our position might have on other cosmological observables becomes even more pressing. The physics is the same: gravitational effects of large-scale density, contrasts, acting on photons and on the expansion rate itself, producing subtle but measurable biases that accumulate over the vast distances involved. Part 15. What the scariest reading gets wrong. Let me turn the light on the most alarming version of this story. The most dramatic interpretation says the KBC void proves lambda CDM is broken, the cosmological principle fails, general relativity needs replacing with MOND, and modern cosmology is a house of cards on a false assumption. There are real reasons for skepticism. The void's depth and extent are contested. The 46% claim comes from galaxy counts in redshift space, which can be distorted by peculiar velocities. Galaxies moving toward us appear closer. Galaxies moving away appear farther. This redshift space distortion can artificially deepen an apparent underdensity. The 2025 velocity field analysis by Stiskalik, Desmond and Bannock found a much smaller void. The true contrast may be 15 to 20%, and at that depth, the challenge to lambda CDM weakens substantially. The 6 sigma tension depends on comparison with a specific simulation using WMAP1 parameters. More recent simulations with updated Planck parameters might yield different conclusions. The tension is real but model-dependent in its exact magnitude. MOND has its own severe problems. It excels at galaxy rotation curves but struggles with galaxy clusters, which still require dark matter even under Milgromian dynamics. The 11-electron-volt sterile neutrino the NUHDM model requires has not been detected by laboratory experiments including Katrin. The model has not reproduced the full range of cosmological observables with lambda CDM's rigor. The cosmological principle is not as fragile as the dramatic narrative implies. Homogeneity and isotropy are statistical claims. The universe looks the same on average, not identically everywhere. Fluctuations are expected. Large voids are expected within limits. The question is whether this void exceeds the limits, and that depends on measurements still being refined. The honest position: we are at the edge of something, but we do not yet know what it is. Part 16. What gravity remembers. There is a deeper layer. It concerns time. The KBC void, if it exists, forms slowly over billions of years. Gravity pulled matter out of the underdense region, into the surrounding web. The void today is the accumulated record of every imbalance in the initial density field, amplified across 13.8 billion years. The primordial fluctuations were tiny, 1 part in 100,000. From those seeds, gravity built everything. The cosmic web is the fossil of those conditions, grown to maturity. A void's size depends on the scale of the initial underdensity and the strength of the gravity that amplified it. In lambda CDM, the growth rate is fixed by the universe's contents and by general relativity. These impose a ceiling on void depth at any given scale. The KBC void, at 300 megaparsecs and 46% underdense, hits above that ceiling. If the observations hold, something about structure growth is not captured by the standard model. The initial conditions may differ from what the simplest inflationary models predict, with enhanced power at specific scales. Or gravity may be stronger on very large scales, as MOND-based models propose. Or dark energy's evolution may have altered the timeline. If dark energy was weaker in the past, gravity had longer to work, allowing deeper evacuation before dark energy took over and froze the structure in place. The KBC void, if confirmed, is not a curiosity. It is a probe of the physics governing structure growth, initial conditions, gravity, dark energy, dark matter. Getting the void right could mean getting all of them right. Part 17. The view from inside the bowl. Let me show you what this actually means for the way we observe the universe. The KBC void, at 1 billion light-years in radius, is so large that every galaxy within several hundred megaparsecs of us, every Cepheid variable, every type Ia supernova, calibrated from within that volume, sits inside the void. The entire distance ladder that produces the local Hubble constant is built from measurements taken inside the underdensity. If the void generates an outward flow of 200 to 300 kilometers per second on top of the Hubble expansion, every distance velocity pair used to construct the ladder absorbs that bias, and the slope of the Hubble diagram comes out steeper than the global truth. The cosmic microwave background, by contrast, was emitted from a surface 13.8 billion light-years away, long before any void existed. Its measurement of the expansion rate is uncontaminated by local structure. It sees the average of everything, every void and every supercluster, every outflow and every infall, averaged into a single global number. One ruler is held level. The other rests on tilted ground. Both are calibrated correctly. Both are reading accurately. They disagree because they are reading different things. Consider a hypothetical observer 1 billion light-years from here, outside the void, on a filament of normal cosmic density. That observer would build their own distance ladder, measure their own local Hubble constant, and find it closer to 67. They would look at our measurement and wonder why we get 73. And if they were clever enough, they might notice the density gradient between their position and ours, and work out the answer. We do not have the luxury of that outside perspective. We are inside the bowl. The only way we can detect it is by measuring the density of the universe in every direction and comparing it to the theoretical average, or by looking for the dynamical signature of outward flow in the peculiar velocities of galaxies around us. Both of these methods have now provided evidence for the void. Neither has settled its exact depth. There is a beautiful irony in this. The cosmological principle was designed to prevent us from treating our location as special. But the consequence of taking the principle too literally, of assuming our local expansion rate must equal the global one, may have been to introduce a bias that the principle itself cannot detect. The cure became a subtle form of the disease. There is another way to think about the void's effect on our measurements that may help clarify the physics. Imagine drawing a sphere around the Milky Way with a radius of 300 megaparsecs, the approximate extent of the KBC void. Everything inside that sphere is in the void. Now draw a series of concentric shells at increasing distances. 50 megaparsecs, 100, 150, 200, 250, 300. In each shell, the density is below the cosmic mean. The galaxies in each shell are moving outward, away from the centre of the void, at a speed that depends on how much mass is missing from the interior. The cumulative effect of all these shells, each contributing its own outward flow, is an excess recessional velocity that grows with distance from the centre of the void and reaches its maximum at the void's edge. When you build a distance ladder using galaxies in these shells, you are measuring their recessional velocities, which include both the Hubble expansion and the void outflow. The Hubble expansion is proportional to distance. The void outflow is also roughly proportional to distance, in a linear approximation for a uniform underdensity. So the two effects add together in a way that simply steepens the apparent Hubble law. The slope of the distance-velocity relation, which is the Hubble constant, comes out higher than the true global value by an amount that depends on the depth of the void. This is a robust, well-understood effect. It is not speculative physics. It follows directly from Newtonian mechanics, or more precisely, from the Birkhoff's theorem analogue in general relativity, which states that the dynamics inside a spherically symmetric shell of matter depend only on the mass interior to the shell. The only question is the empirical one: is the void deep enough for the effect to matter? Part 18. The instruments that will decide. The reason this remains unsettled is data, not will. The surveys needed to measure the three-dimensional density field with enough precision to distinguish a 20% void from a 46% one have only recently become feasible. DESI's final dataset, expected in the late 2020s, will map baryon acoustic oscillations across a volume large enough to measure the expansion rate at multiple redshifts with sub% accuracy. If the void boosts the local rate, the BAO signal at low redshifts will show a systematic offset from higher redshifts. Euclid, launched by ESA in July 2023, is mapping galaxy shapes and redshifts over 15,000 square degrees. Its lensing maps will detect a deficit in gravitational convergence if the void is as deep as galaxy counts suggest. The Vera C. Rubin Observatory will begin its 10-year survey soon, imaging the southern sky repeatedly and cataloguing billions of galaxies for weak lensing and transient detection. Cosmic Flows, now in its fourth iteration, with over 55,000 galaxy distances across 8 independent techniques, continues refining the velocity field map. Alexandre Dupuy and Hélène Courtois used Cosmic Flows 4 to redefine Laniakea boundaries and identify 5 additional supercluster watersheds. The square kilometre array, under construction in Australia and South Africa, will survey billions of radio sources and measure the radio dipole with unprecedented precision, testing whether the quasar-dipole anomaly is real. Within a decade, we will know the answer. The bole's depth will be measured. The Hubble tension will resolve or deepen, and the cosmological principle will be tested on the largest scales we can probe. The Nancy Grace Roman Space Telescope. Scheduled for launch by NASA, will conduct a wide-field survey of the infrared sky with a field of view 100 times larger than Hubble's. Its primary science goals include measuring the expansion history of the universe through both supernova and baryon acoustic oscillations, and mapping the distribution of dark matter through weak gravitational lensing. Roman's wide-field infrared capabilities will be particularly valuable for measuring the density of galaxies in the local universe, because infrared surveys are less affected by dust obscuration and more directly trace stellar mass than optical surveys. If the KBC void is as deep as the K-band luminosity function measurements suggest, Roman will provide the definitive confirmation or refutation. There is also the LSST, the Legacy Survey of Space and Time, to be conducted by the Vera C. Rubin Observatory. Over 10 years, LSST will image the entire southern sky to a depth sufficient to detect faint galaxies out to redshifts of 3 or more, producing a catalogue of approximately 20 billion galaxies. This is not a typo, 20 billion. The statistical power of such a catalogue, combined with the photometric redshift information that will place each galaxy in its 3-dimensional context, will allow the density field of the local universe to be mapped with a precision that no current survey can approach. The KBC void, if it exists at any significant depth, will be visible in the LSST data with overwhelming statistical significance. The combination of these instruments, operating at different wavelengths and using different physical effects to probe the same underlying density field, will provide the kind of redundant, cross-checked evidence that cosmology requires to settle a question of this magnitude. the age of ambiguity about the local density will end. What will replace it depends on what the instruments find. Part 17. The other tensions. The KBC void and the Hubble tension are not the only cracks in the Standard Model's smooth facade. There are other measurements that disagree with lambda CDM's predictions in ways that, while less dramatic, contribute to the growing sense that something may be incomplete about our cosmological framework. One is the S8 tension, sometimes called the sigma 8 tension. S8 is a parameter that quantifies the amplitude of matter density fluctuations on a scale of about 8 megaparsecs. It measures how clumpy the universe is at that scale. Like H0, S8 can be measured in two ways: inferred from the CMB using the lambda CDM model, which gives a prediction for the present-day value, and measured directly from observations of weak gravitational lensing by the large-scale structure. The CMB-based prediction is systematically higher than the direct measurements, meaning that the universe appears to be smoother, less clumpy, at the present epoch than the Standard Model predicts based on the early universe conditions. The significance of the S8 tension is lower than the Hubble tension, typically around 2 to 3 sigma, and it has fluctuated as new lensing surveys have been published. The Kilo Degree Survey, the Dark Energy Survey, and the Hyper-Suprime CAM Survey have all reported S8 values below the Planck prediction, though not all at the same significance. The tension could be a systematic effect in the lensing measurements, or it could be a real signal of physics beyond lambda CDM. What makes it relevant to the void story is that a local underdensity could, in principle, affect lensing measurements made from within it, because the foreground mass distribution shapes the lensing signal. And if the foreground is less dense than assumed, the inferred S8 would be biased low. There is also the lithium problem, the discrepancy between the primordial lithium abundance predicted by Big Bang nuclear synthesis and the amount observed in old metal poor stars. And there is the satellite plane problem, the observation that the satellite galaxies of the Milky Way and Andromeda are arranged in thin, co-rotating planes rather than the roughly isotropic distributions predicted by lambda CDM simulations. Pawlowski, Krupa, and colleagues have argued that these satellite planes are a severe challenge to the dark matter halo model, and that they arise more naturally in MOND-based frameworks where tidal interactions between galaxies create coherent debris structures. None of these tensions individually is fatal to the Standard Model. Each has possible explanations within lambda CDM. But their accumulation across independent observations and independent scales creates a pattern that is difficult to attribute entirely to measurement error or statistical fluctuation. The Standard Model is not failing spectacularly. It is failing quietly in multiple places, in ways that all seem to point toward a universe that is more structured, more anisotropic, and less smooth than the model assumes. Whether these tensions are connected, whether they all trace back to a single missing ingredient in our understanding, or whether they are unrelated quirks that will be resolved one by one as the data improves, is one of the defining questions of 21st century cosmology. Part 20. The long tradition of being wrong about our address. Every major advance in our understanding of cosmic structure has come with the discovery that our position is less central, less typical, less privileged than assumed. Before Copernicus, the Earth was the centre. Before Shapley, the Sun. Before Hubble, the Milky Way was everything. Before the large-scale surveys, galaxy distribution was assumed random. The cosmological principle is the final version of this modesty. It says not only that we are not central, but that there is no centre. Our location is statistically indistinguishable from any other. But notice the argument. The principle was adopted not because we verified cosmic uniformity through exhaustive survey. We cannot survey beyond the observable horizon. It was adopted because assuming specialness always proved wrong, and because the mathematics of a uniform cosmos is tractable, while irregular cosmology is forbiddingly hard. There is a difference between the methodological principle, assume you are not special, and the empirical claim, you are verified as not special. The first guides theory construction. The second requires observation, and observations are now reaching the precision to test it. If the Milky Way occupies a significant underdensity, it would not invalidate the cosmological principle philosophically. Voids are part of the model, The question is whether this one exceeds the model's limits. But it would mean our assumption of typicality, the assumption that local expansion equals global expansion, fails in practice. Our cosmic address has changed before. Earth lost its centrality. The Sun lost its. The Milky Way lost its. Each time the revision was uncomfortable and eventually absorbed. If it turns out that we live at the bottom of a shallow bowl, that too will be absorbed. It is only the discovery phase that stings. The cosmological principle has a deeper history than most people realise, and that history is worth telling because it reveals how our relationship to the idea of cosmic ordinariness has shifted over time. The modern formulation of the principle is often attributed to Arthur Milne, who stated it explicitly in 1933 in his book Relativity, Gravitation, and World Structure. But the idea had been implicit in cosmological thinking since Einstein applied general relativity to the universe as a whole in 1917. Einstein assumed that the universe is homogeneous and isotropic not because he had evidence for this, but because it was the simplest possible assumption and the only one that made the equations tractable. His static universe model was wrong, the universe is not static, but his symmetry assumption survived and became the foundation of all subsequent cosmological models, including the expanding universe models of Alexander Friedmann, 1922, and Georges Lemaitre, 1927. The philosopher and astrophysicist Hermann Bondi gave the principle its name in 1948 and distinguished between a cosmological principle, homogeneity and isotropy in space, and a perfect cosmological principle, homogeneity and isotropy in both space and time. The latter being the foundation of the steady-state theory that Bondi, Thomas Gold, and Fred Hoyle proposed as an alternative to the Big Big. The steady-state theory was eventually ruled out by the discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson, but the ordinary cosmological principle survived and became, if anything, more firmly entrenched. What is often forgotten is that the principle was always understood by its originators as an approximation, not a literal truth. Einstein knew the universe had galaxies and voids. Milne knew it was not perfectly smooth. The question was always about the scale at which homogeneity sets in. The assumption was that on scales above some threshold, perhaps 100 megaparsecs or so, the density fluctuations would average out and the smooth picture would prevail. The KBC void challenges this not by denying homogeneity on principle, but by suggesting that the threshold may be larger than assumed, and that the volume from which we observe the universe may not be large enough to average over the local fluctuation. Part 21. What we know and what we are guessing. Let me draw the lines clearly. What the data tells us with high confidence, the local universe out to several hundred megaparsecs, is less dense than the cosmic average. This is established by 3 decades of observations across optical, infrared, X-ray and radio wavelengths, by multiple independent groups using different instruments and methods. The local void identified in 1987 and mapped in 2019 is well characterized and undisputed. The Milky Way sits at its edge and the void is expanding. What the data suggests but has not settled, the larger KBC void, at roughly 300 megaparsecs and 20 to 50% below the mean, is supported by galaxy counts, but contested on exact depth and boundary. Direct velocity field measurements favour a smaller void. The true density profile is certainly more complex than any spherical model. What remains genuinely open, whether the underdensity fully, partially or negligibly explains the Hubble tension, whether it is consistent with lambda CDM or demands new physics, whether it connects to Desi's hints of evolving dark energy or to the quasar dipole anomaly. These are active research questions with no consensus answers. What is speculative? That the void requires MOND or a specific sterile neutrino. Intellectually serious proposals, unconfirmed with their own unresolved problems. What is wrong? The claim that the standard model is already broken. It is strained. It may eventually break, but the evidence does not compel abandonment. It compels attention, measurement, and the willingness to follow data wherever it leads. The universe has always rewarded patience over certainty. Part 22. the creature in the hollow. We have covered an enormous distance, and I want to end not with physics, but with feeling. You live in a cosmic hole, not a dramatic one. Not a black emptiness swept clean of matter and light. You live in a region that is slightly less crowded than the universe at large, a gentle depression in the density of everything. A shallow bowl whose slope is so gradual that it took decades of painstaking galaxy counting and velocity mapping and X-ray cluster surveying to detect it at all. And yet that gentle slope, that modest dip in the cosmic floor, may have been enough to bias one of the most important measurements in the history of science. There is something beautiful and unsettling about this. The precision of modern cosmology is so extraordinary that a 20% variation in galaxy density on a scale of 1 billion light-years, a variation you would never notice looking at the sky, produces a disagreement between two measurements of the expansion rate that has consumed the careers of hundreds of physicists and prompted serious discussions about the foundations of the entire field. The instruments have become so sensitive they can feel the tilt of the floor. The history of this discovery follows a pattern that recurs throughout science. It begins with an anomaly, two numbers that should agree and do not. Then comes methodological scrutiny, every source of error hunted and tested. When the error proves elusive, the community begins to entertain the possibility that the anomaly is real. Then the theorists offer explanations, conservative to radical, and the observers design experiments. We are in the middle now. The anomaly is persistent. The explanations compete, the experiments are being built. What makes this particular anomaly poignant is the way it touches the oldest question in cosmology. Are we typical? The cosmological principle says yes. The KBC void, if confirmed at its most dramatic scale, says not quite. You are not at the centre of the universe, no one is. But you may be at the bottom of a depression that makes your view of the expansion slightly different from the view 1 billion light-years away. And that difference has consequences. I find it remarkable that the same species which once placed the Earth at the centre of a crystalline cosmos, fixed and privileged and uniquely important, has arrived at a point where the question is whether our neighbourhood is 20% emptier than average. The arc of cosmic humility has bent so far that even a modest departure from typicality feels like a revelation. We have travelled a very long road from Ptolemy. The Vera Rubin Observatory is scanning the southern sky. Euclid is mapping the shapes of distant galaxies from its station at the second Lagrange point. DSI is swallowing spectra by the millions from the summit of Kitt Peak. The square-kilometre array is rising from the red dirt of Western Australia and the Karoo of South Africa. Within a decade, perhaps less, we will know whether the bowl is as deep as the data hints, or shallower than feared, or something else entirely that no one has yet imagined. Until then, you live in a cosmic hole. Nobody told you. But now you know. And the fact that, that you are the kind of creature that can stand inside 1 billion light-year under density and work out that you are in one, using nothing but the light that reaches your instruments and the mathematics that holds it together. That fact is as remarkable as the whole itself. Sit with that for a moment, then look up. The sky is the same sky it was before you knew, but the ground beneath it is a little less certain. And in cosmology, uncertainty is where the next discovery lives. The shallow bowl is, in the end, a metaphor for something larger than cosmology. It is about the relationship between the observer and the observed, about the way the ground you stand on shapes the sky you see, about the difficulty of recognising a bias that is woven into the very act of measurement. Every culture that has looked at the night sky has constructed a cosmology that placed it at the centre of things. The Babylonians saw the Earth as a flat disk floating on the cosmic ocean. The ancient Greeks perfected the geocentric model, nesting the planets in crystalline spheres, with the Earth at the still point of all motion. The medieval Europeans inherited this picture and baptised it, placing God at the outermost sphere and humanity at the centre of creation, midway between the divine and the demonic. Each of these cosmologies was internally consistent. Each explained the observed motions of the sky with impressive accuracy. And each was wrong about the fundamental question of where we are. We like to think we have outgrown this tendency. The Copernican revolution, we tell ourselves, taught us humility. We know we are not at the centre. We know the Earth is an ordinary planet, orbiting an ordinary star in the suburbs of an ordinary galaxy. The cosmological principle is the mathematical expression of that humility. There is nothing special about our location. But the KBC void, if it is confirmed, would add a wrinkle to that narrative. It would not place us back at the centre. There is no centre in a void. A void is a feature of the density field, not a location with special status. But it would mean that the specific patch of cosmos from which we have been studying the universe is, in fact, not typical. Not in some grand metaphysical sense, just in the local density, just enough to tilt the numbers, just enough to make us argue for decades about whether the universe is 13.8 billion years old or 12.6 billion, whether it will expand forever at an accelerating rate or eventually slow down, whether the physics we know is complete or missing something. The instruments are out there now, collecting photons, measuring redshifts, mapping the shapes of distant galaxies. The data is accumulating. Within a decade, the bowl will either deepen or dissolve. And whatever the answer turns out to be, we will absorb it, as we have absorbed every previous revision of our cosmic address. And we will continue doing what this species has always done, looking up, counting what we see, and trying to work out where we are.